In this video, we're going to discuss another concept that one should really be aware of when analyzing differential equations. And it's not a terribly difficult concept. It's not one that we're going to go super deep into, but it's something that's referred to as the interval of existence or the interval of validity. And in many ways, it is related to the concept of the domain of a function, but it takes it a step further because we're not just talking about just random functions now. We're talking about functions that actually satisfy a differential equation or satisfy a differential equation and a set of conditions. All right. So what I'm going to do to introduce this idea is again to do so via a specific example. All right, so it can be shown that the differential equation, and here is the equation that we will use, dy dx is equal to y minus 3 squared, right? So that differential equation has a general solution of the form, and it's this function. So 3 minus 1 over x plus c, where c is some real number. All right. So let's ask ourselves this question. It's a question that we know how to answer, but again, we're going to use this and just look at it in a slightly different way. So let's ask ourselves this. What is the particular solution satisfying this condition? So now let's put a condition there. Let's say the condition is y of 1 is equal to negative 3, right? So what this tells us is that when x is equal to 1, y is equal to negative 3, and then this gives me an equation through which I should be able to figure out what the constant is, because that's how we go from the general to the particular, right? We need some additional bit of information that will say, okay, out of all of these functions, which one satisfies this condition? So let's see what our algebra tells us. So replace y with negative 3, and then I have my general form on the right hand side. And so, and x here is equal to 1. So we'll be able to use some algebra to isolate our c. So let's subtract 3 from both sides. So we have negative 6 is equal to negative 1 over 1 plus c. Multiply both sides by negative 1. We have this. We can take the reciprocal of both sides. So what this tells me is that 1/6 is equal to 1 plus c, and then I can subtract 1 from both sides, and I'll get that c is negative 5/6, right? So what is the particular solution? Well, let's write it down. So this implies that y of x is equal to 3 minus 1 over, and then I'll have x, and it's going to be minus 5 over 6. So that's the function. Let's kind of clean this up a little bit. Maybe write it as a single fraction. Well, actually, let's see if we can just write it without this fraction within this fraction. So let's multiply this top and bottom by 6. So what will we end up with? 3 minus, then I'll have 6 over 6x minus 5, right? And then if I wanted to get the common denominator, so then it will be 3 times the quantity 6x minus 5 minus 6 over 6x minus 5. So Now, what do we end up if we write that in a nice simple form? We'll end up with 18x, and then we have a minus 15, and then minus 6, so that's minus 21, and then that's over 6x minus 5. So this is the function that not only satisfies our original differential equation, but it also passes through the ordered pair 1 comma negative 3. Let's take a look at the graph of this function. Right now, this function, depending on what form you have it in, it's easier to identify some of the key properties. And again, I'm not going to go into the details of plotting functions. I just want to come up with a sketch. If I look at the function in this form, either of these forms where I have the 3 minus, what this tells me is, see, as x gets very, very large, right, this fractional part of the function approaches 0. So y will approach 3 minus 0. So that means y equals 3 is going to be a horizontal asymptote. So I'm going to draw like it's a horizontal asymptote. This is the line y equals 3. And then again, in, let's say, this form or even this form, we can see that when x is equal to 5 over 6, so not quite 1, but just a little bit less than 1, when x is equal to 5 over 6, then we'll have a vertical asymptote, right? So we can kind of put these two things together and you can come up with a sketch. Again, let's say you wanted to figure out the y-intercept. The y-intercept here is, so that's when your x value is 0. You're going to end up with negative 21 over negative 5, so just a little over 4. So it's, it's there. And then, like I said, this y equals 3 is a horizontal asymptote. So here is one part of the function. And then it's going to go off to positive infinity that way. And then the other part now comes up down here, and the x-intercept, that would be the value of x that would make the numerator equal to 0, and that will be 21 over 18, so just a little more than 1. So like if there's a 1 here, so it's going to look something like this. Again, not super detailed, and again, this is not an exercise in detailed sketching, but what I want to come up with now is the sketch of this function, right? And again, you could use some graphing utility to come up with a sketch that looks something like this. So as a function, right, as if I just gave you this, so take the differential equation part out of it, right, so it's just a standalone function of real variables, then this would be its plot, and we would look at it and say, well, yeah, this function has a domain. So we could say, so as a function, right, y of x has a domain of, and this would be, and let me just write it with inequalities, where x is either less than negative 5/6, and that would be this part, right, over here, or x is greater than 5/6, and that would be this part. So if I just gave you this and said, what is, give me a sketch and tell me its domain, this is what you would come up with. But the thing now is, this is not just some arbitrary function that we wrote down. We actually derived this function first by getting the general solution of a differential equation and finding the initial condition that this function passes through. And remember, the initial condition is when x is equal to 1, y is equal to negative 3. So that means it is somewhere. So 1, negative 3 is somewhere here. So I'm just going to say that this is x equals 1, and then this is y equals negative 3, right? So actually, when we look at this, this function, because of the vertical asymptote, is kind of broken into two pieces. They're often referred to as branches of the same function. But only one of these branches actually passes through the original, or I should say the initial condition. This piece over here, right, when x is less than 5/6, it does not pass through the ordered pair 1, -3, only this one. So now what I'm going to do is just kind of highlight this part of the graph. Oh, my function, in fact, let me start over here. So let's see, a little bit shaky. And okay, so a little bit better there. So that part of the function now. So as the solution to the initial value problem, that is, in other words, satisfying the differential equation, satisfying the initial condition. So to the initial value problem, y of x, so we don't use the word domain now, we use the phrase either interval of existence or interval of validity. So in other words, for what values of x is this function, or now this solution, actually valid? And it is, so y of x has an interval of existence or validity, right? Validity of x greater than 5/6. Right? So that's the subtle difference between just, again, the general concept of the domain of a function versus the interval of existence of the solution to an initial value problem. So it's kind of like process-wise, it's not a huge step, but it's more a conceptual step that we're making. So let's actually write down formally what the interval of existence is saying. So the interval of existence of a particular solution, so of a particular solution to a initial value problem, so I'll just say IVP, is the largest, and it's usually an open interval, so I'll put it in parentheses, the largest open interval and that interval has to contain the initial value, which in this case is x equals 1. So containing the initial value, right, on which the solution satisfies the differential equation. Right? So when we're talking about the interval of existence or the interval of validity, not only are we thinking, okay, for what values of x is this function defined, not just that, but in addition to that, it has to be defined. Well, not just defined, but if you think about it, it has to be continuous. Because if the function satisfies a differential equation, then the function has to be differentiable. And if the function is differentiable, calculus tells us that it has to be continuous. So the function has to be continuous, right? And it has to pass through the initial condition. And only one of these two pieces would do that, right? So it's really just a deeper use of the concept of the domain. It's just that it's not just where, in this case, it's continuous, right? But where does it also satisfy the the initial condition? And in this case, since our initial condition is 1 comma negative 3, only this branch of our solution satisfies it. This piece never passes through um, that ordered pair, even though it's essentially, you could say, opposite sides of the same coin. Well, we want this particular side because this is the side that passes through our initial condition. Let's do another example using the same general solution, right? So let's ask ourselves this question. So what is the particular, in fact, yeah, I was just going to do the interval, but let's again find the particular. So what is the particular solution satisfying, and let's pick a different condition now. Let's pick y of negative 2 is equal to 10, and then we're going to state its interval of existence. Right, so we're going to find it. So we're going to find this, and again, not just think of it as a function now, but the fact that it has to satisfy this initial value problem. All right, so let me just, for completeness, let me state the general solution. This is what we have, right? So then let's do our algebra. So when x is equal to negative 2, y is equal to 10. So that gives me this equation. 10 is equal to 3. So 3 minus 1 over, and then my x value is negative 2. And then I have my plus c, which is what we're trying to figure out. And then we're going to use pretty much the same set of algebra that we did earlier. So subtract 3 from both sides. That gives me 7 is equal to negative 1 over negative 2 plus c. Multiply both sides by negative 1. We have this. What do we have here? So then negative 2 plus c. Take the reciprocal of both sides. So then this gives me negative 1/7, and that's equal to negative 2 plus c. Add 2 to both sides, so that's 14 over 7. So 14 over 7 plus negative 1 over 7 gives me 13 over 7, and that's my c, right? So therefore, what is our particular solution? It's 3 minus, and then it's 1 over x plus, and then we have 13 over 7 there. So again, like we did earlier, let's go ahead and write this as a let's say a single fraction. So first I'm going to multiply this fraction, the numerator and denominator, by 7. So I'll have 3 minus 7 over 7x plus 13. Get our common denominator, so that's 3 times the quantity 7x plus 13 minus 7 in the numerator, and now my common denominator is 7x plus 13. So let's see, so we got 21x. So we have 21x, and then we have plus 39 minus 7, so that's plus 32. And then what do we have over here? 7x plus 13. All right. So that's the particular solution. So now let's think about it. And again, you don't have to do the graph per se, but I like to do the graph. So I'll show you the sketch of this one. And just like before, in our first example, this particular solution has a horizontal asymptote at y equals 3. So still there. But now the vertical asymptote is at a negative value. It's in fact negative 13 over 7. So I'll label these in a bit. So this is, let me write it up here, x equals negative 13 over 7. And here y is equal to 3. And as far as the, let's say the y-intercept now, when x is equal to 0, the y-intercept is 32 over 13, but that's less than 3, so it's now down here. And then as far as the x-intercept is concerned, it's going to be negative 32 over 21. So it's not as it's greater than negative 13 over 7. So it's basically here, right? So this is what it looks like. We have a part of the function like this, right? And then again, this is just as a function. If we were just sketching this function back in the good old days of algebra, this is what we would come up with. And now, so again, what we can say, so if you want to, again, distinguish between the domain and the interval of existence, the domain in this case, it's all values of x that are either less than negative 13 over 7 or x is greater than negative 13 over 7. Obviously, you could have stated like this, x is not equal to negative 13 over 7. But now this is where we have to consider the initial condition. Remember our initial condition for this, what was it? When x is equal to negative 2, y is equal to 10. So negative 2 is less than negative 13 over 7. So it's basic. It's close, right? But it's basically here. So let me do this. Now, obviously not drawn to scale at all, but here this would be the y value of 10, and then this would be your x value of negative 2. So of the two branches now, this branch over here, again, right? This is the part of the particular solution that we're interested in for this initial condition. So now we can say that the interval of existence or validity for this particular solution is all values of x less than negative 13 over 7. So it's kind of like we had to figure out, for instance, if the function had some kind of, let's say in this case, vertical asymptote that causes the function to split into these two branches, then the question then becomes which of the two branches not only satisfies the differential equation. We know it's going to satisfy the differential equation because it's a part of the general solution. But then now which part of the function also satisfies the initial condition? So which one of these passes through the given ordered pair? And the largest interval over which that happens, right, is what we define as our interval of validity. So again, it's building on the concept of domain, but it's not just, okay, where is the function defined, but where does the solution satisfy the differential equation and the initial condition, right? So just another interesting concept that's related to to differential equations. And again, it's something that we could go a lot deeper into, but we won't. I think this is really a good introduction to the concept, and then we will just move on and keep solving and keep analyzing these differential equations, because what else are we going to do? I don't know. I think it's a lot of fun. Hopefully you're enjoying it and you're finding it interesting, and you can't wait to see what comes next. Well, check out the next video and you'll see. See you then.